Hey friends, I'm Carmen and I'm one of the educators at Curiodyssey. Today, I'm going to be trying one of our at-home science experiments for kids called the solar oven. Now, what's a solar oven? A solar oven is a device that uses energy from the sun in order to heat something inside. It's a lot like a regular oven, except it doesn't use any electricity. It's a pretty cool device that you can engineer from some everyday materials you might be able to find in your own homes. Alright, so I figured that before I try to build my own oven, I should check out what a regular oven looks like, and here's a little tour inside. Make sure you always ask for permission at home before you use the oven, so that way you can do it safely. So inside of the oven, what I noticed is that up here there's a heating element. This is what gets warm when I turn on the oven. There's another one right here at the bottom, and you can control whether both of them are working at the same time, or just the top or just the bottom. In the case of our solar oven, since we're going to be using the sun, we're going to be having heat coming from above. So I think it'll be most similar to how this heating element interacts with our food. Now, inside our oven, let's go and get something to put inside of our oven. Okay, we have some food now to put inside of the oven to see if we can notice it in action. Here's my pan of Brussels sprouts, and I'm gonna slide that into the rack. Now, what's going to happen is the air around the food is going to get heated by these elements. Some of that heat from the air is going to transfer to the food. Meanwhile, the pan that the food is on is also going to get hot. It's metal, so we'll definitely use our pot holders when we go on in to get this out. Since this metal is going to heat up, there's a second way the food is also getting warm. The direct contact with the oven pan, in addition to the warm pocket of air in the oven surrounding the food, are what's going to cook it. Those are two processes called convection and conduction that we'll want to think about when we're building our own solar oven. Let's go ahead and leave that to cook, and I'll catch up with you in a little bit. Okay, we're ready to take our food out of the oven and see what we learned about how ovens work. PPE, got it covered. So our food's been in here for just about 10 minutes, and it looks like our sprouts are completely roasted. Take a look right over here. Fun fact, all of that nice browning that gives your food flavor, that's from a chemical reaction. It's called the Maillard reaction, and it only happens at temperatures above 265 degrees Fahrenheit when there's an amino acid and a sugar reacting due to the heat. Now, while I was letting these cook, one of the things I was wondering is, when we make our solar oven, how high will the temperature ultimately end up being? With our solar oven, I wonder what I'm going to do to keep any of the heat that I harness from the sun from escaping out of the oven instead of going into the food. Sounds like a good question that we can do some testing to figure it out. Alright, let's start getting set up. Here we are at our Curiodyssey at-home science experiments for kids section. Definitely check this out after you ask a grown-up if you can go online. We're going to want to take a look at our how to make a solar oven activity. It looks like over here in our instructions, we're recommended to have some sort of a box, something reflective, something clear, and a knife or sharp scissors. I also see that below right over here, the instructions call for some black construction paper. Now, I don't have all of these things at home, and I wonder if you might be in the same situation. So let's get creative and let's do a little bit of improvising together. Wow, we sure found a lot of stuff laying around the house. I hope your search was just as successful in finding some cool things that you could use to build a solar oven. Now, I've got a bunch of stuff to look through and narrow down the options. So while I imagine the idea I might want to try, I'm going to pick out a few materials that I think will work before I start building. we'll see how that goes. And I think it's about time to start designing what my official test is going to be to see how our solar oven does at trapping and transferring heat. Let's go looking around the kitchen lab to find something that we can heat up in this little oven. I found this cutie, a marshmallow, and some popcorn kernels. So here it is. Here's my idea about how I think I can use a marshmallow instead of a thermometer to analyze how the oven is able to trap heat and transfer it to another object. From my own experience, I know that marshmallows change with heat. I know that they change texture from bouncy and springy to squishy and oozy. I know that they change shape from holding this cylinder to going flat like a puddle if they get exposed to a lot of heat. I also know that when you poke a marshmallow at room temperature, it bounces back, and that when you poke a marshmallow that's been heated in the oven or the microwave or over a fire, that it doesn't bounce back, it kind of just stays squished. I'm gonna head outside to experiment with different angles of the sun using my reflective surfaces to see if I can start collecting some heat and notice some changes with our marshmallow thermometer. Okay, it's been 10 minutes and I'm going to open up to see if I can notice any differences in our marshmallow after it's been sitting in the oven. So right here on the outside, I do notice already that this air pocket does feel warm. Oh, and right here inside, feeling this cloth bag, it's also warm. So here's a close-up look at our marshmallow, and let's do a few tests. So it looks like the shape, it got a lot more puffy, and let's try to press it. Whoop! And look, it stays pressed in. So it has partially melted, and that is, I guess, my first measurement on a marshmallow test. Let's compare that to a room temperature marshmallow to see if we can make a few more ideas and observations about how this changed. So here is our marshmallow that was in the solar oven compared to a room temperature marshmallow from the countertop. So as you can see, the room temperature marshmallow, if it gets squeezed, it bounces right back, and it has this nice even cylindrical shape. Now, what I saw happen with our oven marshmallow is that when I took it out of the oven, it was a lot more round, a lot less cylindrical, and then when I pressed it, it flattened right there in the middle, kind of like a little donut. And it's staying in that shape. So now I wonder, this was the marshmallow in there for 10 minutes, how many minutes will it take for the marshmallow to flatten on its own without me needing to squish it, or will that ever happen? So I'm going to run a few other tests and even make a couple of other oven designs to see if I can report back some more thorough results about using our marshmallow as an index of temperature change. As it often goes in science, after tinkering around and trying to make a few more types of solar ovens, I ended up with more questions than answers. one of the things I ended up wondering was what really does make the best solar oven? As I was creating some new designs, I pointed out some of the strengths and weaknesses that I noticed in my own prototypes. When you're thinking like an engineer, it's really important to make sure that you're not afraid to change things as you go along and to be a little bit critical of what you create so that way you can help yourself to improve. So starting with this design that I made, you saw that I had a little bit of trouble prototyping it in the first place. I wasn't quite sure how to get things to stick to the metal baking pan, and that's why I finally switched to a rubber band instead. A question that I came up with this oven is, well, it does seem like it would work really well, but it's not so convenient for getting things in and out of the oven. I would have to undo the whole rubber band, which will be hard by myself. So that's one weakness that I decided that this design had. But I really wanted to try to use the baking pan because I've heard that metal is a good conductor of heat. So I thought that would help to transfer more heat to whatever was inside. So that's this version right over here. Here is another little prototype that I came up with using a mailing envelope. I discovered that when I opened a little package, that even though the envelope was white, when I took apart the sections, it had a layer of black plastic. So I was able to take that out and use the bubble cushioning in addition to this plastic that was lining it. I also found this snack bag that had a metallic lining inside, and I thought that could be a good reflector. So here is how I imagined the design would work, and I haven't even put this one outside because I anticipated an interesting problem given the area where I live. But if you were anywhere near the wind, I think it would just fly away unless you were trying to heat up something like a rock, which is not what we're using in our case because I have marshmallows. So that's a little bit of feedback for my own designs as I was trying to think like an engineer. And of course, in science, nothing is ever quite as straightforward as it seems. I've run into yet another question, and I'll show you what happened outside to see if you can figure out why. Let's go take a look. Hello, sky full of clouds. This is not the perfect weather to be trying to use a solar oven. Whenever you're a scientist who works out in nature, it's part of your everyday to expect the unexpected. So our little bout of cloudy weather outside is nothing to be discouraged by, but it's something that'll push us to think like engineers and innovate a little bit farther. I've come up with a new question to help kind of deal with this unpredictable weather situation. At first, my goal was to see if I could melt the marshmallow flat in the solar oven. And now I realize that if the weather patterns are going to change from cloudy to sunny so quickly, I might be waiting a real long time to be able to melt that marshmallow completely flat. So I think I'm going to just revise what my test is. I realized that 10 minutes is a pretty good time period to be able to notice a real difference in the marshmallow. So I think instead of waiting until the marshmallow is flattened, I can use those 10 minutes and make the most of them. I think I can combine some of the aspects of these other ovens into my original design. For example, what would happen if I used this foil in addition to the mirrors to help reflect the sunlight into the oven? I'll leave the conclusion of this experiment up to you. I challenge you to go outside, try out a solar oven, see what happens, and notice what you could do to improve your design. Keep experimenting, have fun, and I hope you can make some brand new discoveries with a contraption that you could build all on your own. Have fun, scientists, and we'll catch up with you next time.